Let's hear, what do you guys think the difference is between hotter and colder liquids is? Jonathan?
Well, when I'm looking at this, the colder it gets, the less active we go. So that way, I think that how it makes it turn to ice, the less active it is. And the more harder it gets, the more active it becomes. So they just keep moving fast and they just go bouncing each other. So water, like while they're boiling, there's bubbles and it's moving.
Okay. Yeah, that's a very good answer, Jonathan. So, for those over here who should have been listening a little bit better, okay, Jonathan said that he noticed when it's colder, they're moving a lot less, and he thinks that that could be why it makes ice eventually. And when it's hotter, they're moving a lot more,
That makes it boil.
and that can make it boil. Okay.
That's what I said.
Okay.
I figured that out.
Eiley, you have anything to add?
You can't make like, okay, so like when you set it on hot,
Oh, sorry, 1 second, Eiley. Guys. All right, Eiley,
when
go
you set
ahead.
it on hot, they like are all over the place, and when it's on cold, they're really close. Instead of make ice, they have to be all really close for it all to freeze. But if you're like that, and then try it, it wouldn't work because it's all out everywhere. And you can't just like that.
Okay, good. You're identifying that they need a lot of space when they're hot, right?
Yeah.
That's good, Eiley. All right, yes, Maylee. We're going to be putting them back here in just a second, okay? We'll take care of that when we do that. Okay? Anything else that we have to add? So, this idea then that when it's colder, you have less energy, they're moving around less, they're close together. When it's hotter, they're spread apart more, they're moving around a lot faster. We have a specific word that we talk about when it comes to moving faster or slower, and that is kinetic energy. Okay, so write this down in your notebook. Kinetic energy is how fast or slow particles are moving.
No, that's how you spell kinetic.
So how fast or slow particles are moving. That's kinetic energy. And so right here, we're going to be done with the iPads for now. So as you get done writing this down, go ahead and put your iPad back.
Please come to the office.
And then I'll take it.
And in the middle, it would kind of like, they're kind of like our little bit harder because they're kind of longer everywhere. A little bit longer.
As soon as you get done writing down the kinetic energy and its definition, put your iPad back in the cart. Baylor.
Yeah.
Eiley, did you get this written down already? Yeah, go ahead and put your iPad back then, please. Carly,
Yes?
did you get yours down already?
Yeah.
And whose iPad is this one?
Not mine, I have mine. Run!
Go ahead and put it back, Carly.
Oh, it's turned off. Oh, so.
All right, so we're going to go ahead and get moving on. We got our iPads back. Okay, so who can give me some examples of kinetic energy either going up or going down in real life? Something that would happen that would cause particles to be moving faster or slower. Yeah, Jonathan?
Airborne, they use the fire to raise the balloon.
Okay, air balloons using the fire, right? That creates more kinetic energy with our air particles, which makes the hot air balloon go up. Good example, Jonathan. What other examples can we come up with? Kinetic energy either going up or down. Lydia, what do you think?
What?
Example of kinetic energy either going up or down in real life. Like Jonathan just
Maybe
gave us.
when things float, like then the kinetic energy like moves it up, I guess.
Okay, and what would happen? What we want an example of it going up or down. Like Jonathan said, when you pull the flame on the hot air balloon, you're making kinetic energy go up by having the flame on. What's something that could make kinetic energy either go up or down?
I don't know, like a lighter maybe?
Okay, like a lighter, and just lighter to what?
Just a lighter, like a.
So just turning on the lighter.
Turn
Okay.
on the lighter.
Yeah, that would produce an increase in kinetic energy. Tess, you have another example?
Well, I was just gonna say just fire.
Okay.
Like the flames go up, not down. No.
Okay. So yeah, fire in general will add kinetic energy to particles surrounding it. What about getting less kinetic energy? Baylor?
When you don't pull the thing down in the hot air balloon. Oh my gosh.
Okay. That would be not adding or taking away kinetic energy. Yes, Carly?
When you turn off a lighter, it'll make it go back down.
What will make it go back down?
The flame will go away, so it'll go back down because there's nothing pushing it up. And you know, there's no gas.
Okay.
There's no gas. There's no gas.
You're on the right track there, but you're actually missing something. Once you take the flame away, you stop adding kinetic energy, but you don't take it away either at that
Well,
point.
you can like take your hand and like knock it back. What? Like, okay, if it's up, and then you can. You're just yeah, but oh, it's a flame. It'll be like my brother. So.
We'll come back to this thought here in just a second, okay, Carly?
Okay, but actually makes sense to me.
Yeah, we'll talk a little bit more about it though. Let's hear what Jonathan has to
Oh,
say. Okay, so Jonathan brought up the North Pole and the South Pole, right? They are really cold, and so if water's there, they get really cold and they freeze, right? That's an example of kinetic energy going down. So coming back, Carly, to what you were talking about, if you do this, right, you can get rid of some of that heat that was surrounding. So like fanning something off to make it cooler, which then would create the kinetic energy going down. Okay.
No, it's because you weren't explaining it.
Okay. Yes.
Tess told me to say something. So, does Mother Gothel have power over kinetic energy? Because she just goes like.
I don't know what you're referring to.
Entangled? Mother Gothel, she's like, she has these candles and then she's like, I don't know. I just was decorating. So does she have power over kinetic energy?
She goes like,
Perhaps. Is she like putting out the flames is what you're talking about?
Yeah, so she has power over kinetic energy, right?
Well, so she's affecting the kinetic energy by putting out the flame.
Does she have power over it?
Okay, Baylor.
So you like so when it was like really cold when we had it was like a cold spell for like a week. I went outside and I boiled a bunch of water and it got really hot, so all the kinetic energy was bouncing around and stuff. And then I walked outside and I threw it in the air and then it froze in midair. And then so then like it went from like hot kinetic energy to cold kinetic energy. Like
Really fast, you're right. Yeah, and that actually, yeah, that actually has some other things at play as to why it was able to switch from high kinetic energy to low kinetic energy really quickly. Part of that is when you're spreading it out, you're making a large surface area, right? But there's a couple of other things that we may not go in right now, but that is a good example of losing kinetic energy really fast. Okay, so we're gonna bring it back together. Okay, so 3, 2, 1. Okay, so we're gonna bring this back. Yeah, Cardi.
Okay, what happens if you, what would happen if you put like, what would happen if you put like a lighter that's lit into a freezer? What would happen to all the kinetic energy?
Well, if you could
It
keep the
freeze.
lighter on, I mean, it would probably eventually go off, but it would be just kind of going back and forth, be a tug of war between
Who would
heating
win?
and cooling.
Yeah, who would win?
Whichever one has the bigger energy source,
But,
which is the freezer.
well, what if we just put it in like a little mini tank?
Then it would depend on whichever has the more energy source.
What if you put a big fire that you kept on keeping on in a huge freezer? Which one would win?
Like I said, it's whichever has the most energy.
Well, which one do you think would have the most energy?
I'm not 100% sure. Usually the freezer probably, because it's plugged in and it's got a constant energy source. Okay,
But what if it's
so we're gonna move on. So everyone's attention back up front. Okay. So bringing this all together, kinetic energy, how fast or slow particles are moving, and we are looking for what is the difference between hotter and colder liquids. Okay, so
iPads again?
how does these two concepts connect between our hotter and colder liquids and our kinetic energy? Jonathan?
We can say the harder it is, the more active the mass can be, or the colder it is, the less active.
Okay, good. The hotter it is, the more active or more kinetic energy. The colder it is, less active, less kinetic energy. So now we've had a simulation where we've been taking a look at this concept and we're starting to learn it. Now we're going to test it ourselves. Okay, and the way we're going to test that ourselves is we have up here hot water, cold water, and warm water. Okay, this is going to be titled Food Coloring Lab. Okay, so go ahead and put that title down if you haven't already. Food Coloring Lab.
Oh, wait, so a new page? Is it like Lid Lab Love?
You can work on what you've been doing so far or a new page, either way.
Lid Lab Love 1?
Food Coloring Lab. And so we're going to use our 3 cups. We're going to have hot water in one, cold water in another, and warm water in the 3rd cup.
Where does the food coloring come in?
Now, if we have hot water, what would we say about the particles in here? Do they have high kinetic energy or low? Yeah, okay, Carly, good. They're moving on really fast. They have a lot of kinetic energy. Okay, what about my cold water?
Oh, they're moving like slow. They don't move that much.
Okay, good. Alright, so they're slow moving, not going very fast. My warm water somewhere in the middle, right? So, if we were to put food coloring into my hot water versus putting food coloring, Shaylee and Timmy. Okay guys, we got off task. I need you guys to bring your focus back here. Thank you. So we take our food coloring in our hot water versus our cold water. What would we expect to happen that would show us the difference in particles moving? If hot water has faster particles and this one has colder, what would we expect to happen to the food coloring? Be different.
It would get mixed around faster in the hot one.
Okay, so as you say, it would be mixed around faster in the hot water. And so that would be a really good thing to look for. And that would prove to us whether or not what we're learning is true, if that simulation showed us correctly. So one person from each group, go ahead and come up and grab your 3 cups. Another person, come up and grab some of the water, and we're going to get our stuff in here. Okay?
Food coloring. Did I get the food
I'll do the food coloring.
So our group should get it at the food coloring, the fun. Oh, I need a measure.
Just pour them into the closed cups. Okay, so we're pouring the water and then passing it to anyone who doesn't have it yet. Okay, we should be done in like 2 minutes. Okay, so we're getting this done in 2 minutes. Okay, warm water's over here.
I need the cold water. Hold on. Wait, do we just start with hot water?
One hot, one cold, one warm.
Wait, where's the warm water?
Warm water's right here.
That is perfect. No, it's not. That is perfect. Eileen, is that even? Come down here. That is perfect. Yeah. This is not warm.
Cold water, we got some over here, over there. Okay, we're down to a minute. We need warm water to keep our
This is warm water. Cold water has ice
warm
and
water,
hot
I think,
water.
is back there.
Alright, tell me if this is even. We have hot water. Wait, where's the warm
Oh,
water?
Baylor has warm water.
That's perfect. That is
Right
warm.
back here.
I can't even stand that is like insane. That's warm, not room, cold. This isn't warm. Alright, what do we do now? That's like stuff. That's like, oh wait, no, that's not. The high school.
Okay, as hot water and no one else needs it, bring it up here. Okay, cold water's right here. Okay, we're down 30 seconds. We're gonna finish up in 30 seconds here. Right here. Good, good. Okay. Okay, we're heading back to our seats in 3, 2, 1. Okay, I see everyone in their seats except I got one person who needs to get there. Thank you. Okay, your attention up front. So what we're gonna do now, we have one hot, one cold, and one warm. I'm gonna come around with some food coloring. I'm gonna put one drop in each. What I want you guys to do is do not touch the cups. Don't stir them, don't bump them, just leave them there, but make observations, okay? What do you notice about what's happening? Okay, look at different points of view at eye level or up above, and just focus on what's happening with my food coloring, okay? I'll do the food coloring. Here we go. Okay, make sure you're paying attention.
Oh, I'm paying attention. That's cool. Oh my gosh, that's
Okay. Carly, Lydia, here we go.
That's hot.
Paying attention.
No, I can't bump the table. Moving the water. Holy, it's loud.
Okay, make sure you're watching it as it goes.
It looks like you. Oh, that's cool. Oh my god. That one melts.
Okay, here we go. We're paying attention to what's going on. Ready?
I want to write that. That's so cool though. No, it's not. It's like a slide. It's like a base. It's so wow. She's lying. She's lying.
Okay, so I want you to be writing observations down, please.
Okay. Do you have blue? Ours was cool. Is cooler.
what happens.
Like they're all on this far side. It's like the string of food coloring.
Our cold one is still has like strands coming down.
Do you think the cold water is gonna turn red?
Hey, he told us not to touch it.
Okay, so what are we noticing here? Go ahead. Okay, so are we proving our simulation true then? Riley, back to your table, please.
Okay.
Let me go ahead and sit down. Not yet.
Whoa! Oh my gosh! This is actually like.
You're not allowed to do this. This is
Whoa!
that. How did your guys
Oh, this is starting to go up. This is spreading out.
Look at it like this.
Look.
Here and go like that.
Don't throw it!
Okay, is there anyone who still needs a little bit more time to write down some observations? Okay, a couple people. So I'm going to give you another minute or two to write down some observations. Then I have a video to show you. Okay, so make sure you get them written down. Go ahead and back to your seat, Carly. Okay. Not yet.
No, not with my baby.
Okay, Carly, in your seat.
Carly, in your seat.
Both Carlys.
Oh,